Hi, welcome to the next video. In the previous video we were processing data in Chrysalis Pro, and now we are going to use this processed data to solve, refine and finalize a crystal structure. Okay, so we have the ins file. We're going to drag it over the OLX2 icon to open the program. Some advertising, cool. Okay, so OLX2 shows us its main, everything's fine? Yeah, its main body. Okay, so we have the cell parameters, everything here. We have the value of rint, ri over sigma, so we have quite strong data. Resolution is pretty good. It's fully complete data set. Okay, so let's go to work. We can now solve the structure. If you linked your Shellix software to OLX2, we can use Shellix to solve it. And I'm going to solve it right now. Ooh. So, okay. Looks almost okay, but these are octaloxy side chains, so we're going to put oxygen here. And yeah, good in general. So we can now click refine. Refine. And we are refining our model isotropically. As you can see already, we can see that on the electron density map we have a lot of peaks which are in the positions where the hydrogen atoms should be, so it actually looks pretty good, right? But hydrogen atoms will do it later. What do we want to do now? So if we scroll, we are getting rid of these Q peaks, electron density peaks. So now, if we click here, or just type Anis, and click refine, or do Ctrl R, I'll do Ctrl R, we are doing an isotropic refinement. I think I need to change the view to an isotropic because something is wrong. Something's wrong, I don't know what. Oh, I forgot to change it here to shell XL. Okay, now refine. Okay. And again, Anis, Ctrl R. Okay, so our anisotropic refinement provided us quite a good model. These ellipsoids from these carbon atoms in the octal chains, they are slightly elongated, but it's not a huge difference. It's some thermal motion in the structure, it's not terrible, so we don't need to refine it as some disorder, right? It's just a feature of the structure, some flexibility in the side chain. And also you can notice that the last atom, its thermal movement is largest from all of these, because usually the terminal atom tends to move more, right? But yeah, in general everything is fine. We can now, just to see everything better, do kill $Q. We'll, by doing this, kill the Q peaks, we won't see them anymore. And if you now input command grow, we will see the whole molecule, which is great. Nice, porphyrin. It's surprising that this octaloxy porphyrin, the side chains, actually crystallizes pretty well. You would expect that these octal chains would be some terrible to crystallize, but apparently it's pretty good, at least in this particular case. Okay, if we type fuse, we'll go back to the asymmetric unit. So we are now working on the asymmetric unit. So the thing that is worth doing is to name the atoms. So I'm going to start with number 1, type C, and I can now name them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, let's say this way around, 13, 14, 15, 16, 17, 18, come on, 18, 19, 20, 21, 22, 20, oops, 23, 24, 25, 26, 27, 28, 29, 30, 31, and 32. Okay, now do the escape. And alternatively, to name something, you can just press on this atom and input name, let's say N1. That one will be name N2. That one will be name zinc 1. That one will be name O1, and that one will be name O2. We can now click refine. It will refine it, we'll get new names already, and then we can also do the sorting to make some better looking ints file. We do sort, it now sorted everything, refine. Okay, now if we can either go here, we can see already some list of atoms, right? So they are all of them, yes, all of them, except for zinc, which sits on inversion center, I think. All of these are fully occupied. That one is on special position, so it's half occupied. Is the constraint that was put by the program automatically. All of these are on general positions, so they are fully occupied, so this value is 11. Okay, now that everything was named, we can add hydrogen atoms. We can either do that by going to refine, toolbox work, and click add H, or we can also click input command hadd, and it will add hydrogen atoms. Control R to refine, Control R, cool. You can see that the R factor dropped quite drastically to 3.18%. We can apply weighing scheme, Control R, Control R, and now if we click ACTA, it will actually save all the data as a CIF file that we need later to finalize it. So let's do it again. We can see that the weighing scheme is not green yet. Now maybe it will be. Wait, it still haven't finished. Okay, now it's green, so everything's okay. We can have a look at the report options. And now, as I said, CIF-OD file that we generated during data processing contains all the necessary information. So we can just use the information from the CIF-OD file. Great. Collection. Here you can input your details, right? Crystallographer's details. I don't have my details here because it's not my computer. Okay, so again, submitter, operator, you can just put your name here. Crystal. It's something that we should do, otherwise CheckCIF will be complaining. Color. In this case, I don't know if you remember from the processing video, we can say that it was a clear, well, let's say light red. And it was a block and some dimensions, well, I'm not going to check it, let's say it's 0.28, 0.14 E, and 0.05. Okay, preparation details. When I prepare, well, CIF files for publication, They are part of some other paper which includes the supporting information with all the synthetic details. So I just usually say as described in the main text. Okay, crystallization details. In this case, it will be in the zip file. It's useful to write it. So that one was crystallized by slow evaporation of a solution in a mixture of dichloromethane and methanol. Crystal mounting. Most people don't really write anything down here. I usually like to specify that it was a meter gen 200 micron loop, and I also, just in case, write that in this case for mounting the crystal I used this oil. Okay, that's not relevant. It's just showing us image of our crystal. We can play it if you want. Okay, diffraction. That's something that is important to write down if you have, for example, some disorder. If you basically did something in the refinement which is different than what we've just done, so something atypical. So let's say you have disorder of some third butyl group, so you would here now describe that. Oh, there was a disorder of third butyl group, so I split them into two parts. I applied appropriate SADI restraints on 1,2 and 1,3 distances, and then also restrained ADPs to be similar using RIGO and SIMU, blah blah blah, things like this, things like that. Absorption corruption, it knows because it can read it from the CIF-OD file where it's all written. We're not doing anything here. Okay, so I will do refine again to save all these things that we've just inputted. Okay, and now we can have a look at the check CIF. Let's have a look. It's always important to look at the check CIF and see whether there are any errors. There will always be some, but if that's something terrible, it's better to resolve it. It always takes some time. Uh, 2 hours later. Okay, we got something. Okay, so we can see all the information here about the unit cell, space group, formulas, blah blah blah, density, absorption coefficient, R factors, and now. So we have one, wow, it looks pretty good. We have just one sea level alert, non-solvent residue. If you open it, instead of as PDF, as HTML, you would be able to click on this alert and see at the description what could this mean. In this case, it's probably just some thermal movement in our octyl side chains. That's why the minimum and maximum displacement parameters are the ratio is a bit large, and G level arrays that provide us some information. Well, nothing really to be worried about. It's nice that we have a lot of carbon-carbon bonds with positive residual electron density. It means that we have strong data and we can see electron density in bonds, some missing reflections, but it's just alert level G. Yeah, that's probably something behind the beam stop, right? And that's just some information like that valency is probably 2. which makes sense because it's a zinc 2 porphyrin. Yeah, so basically everything's okay with our checksif file, and the data is more than appropriate to publish in the Cambridge database. So if you'd be preparing this file for publication and you need to attach checksif file to the submission to the journal, you probably want here to have a name of your compound, like in your manuscript, right? So for example, I don't know, zinc porphyrin. So how can we do that? We have to do that by just going to the CIF file. We can open it with Notepad. And here, data, we can input whatever you want. Let's say zinc porph. And save. And if we did checksif again, zinc porph would be the name of the data block. Okay, I hope it was useful. Thank you very much for your attention. In the next videos, we will look at some examples that involve disorder. That video was basically to show you how to refine a structure and finalize it and then run checksif. Thank you very much for your attention.